Look at this Cartesian coordinate plane. When we draw two distinct lines, the solution to their system of equations is this exact physical point where they cross. While this graph shows us where the intersection is, plotting points by hand has its limits. If the lines cross between the grid lines or at a tiny fraction, a pencil and ruler can only give us an approximation. To find the precise coordinates, we need to use algebra. This is the standard mathematical format: two equations stacked together. A single equation with two missing variables, x and y, can't be solved alone. To solve both at once, we temporarily remove one. We have two tools for this: substitution and elimination. Look at the variables in this system. In the second equation, the x has no coefficient, standing entirely on its own. This solitary variable makes substitution the most direct path forward. We start by rearranging that simpler equation to isolate the x. By moving the y to the other side, we define x as being equal to y plus 1. Now we have a specific value we can plug into the other equation. We take that expression and literally substitute it for the x in our first equation. After distributing the 3, we get 3y plus 3 plus 4y equals 10. Combining the terms and solving for y gives us a result of 1. Be careful here. It's easy to see y equals 1 and think you're finished, but you found only half of the intersection coordinate. An intersection requires both an x and a y. To find the final coordinate, we take that y equals 1 and plug it back into our isolated x equation. This reveals x equals 2, giving us the full answer, 2, 1. You can prove your answer is correct by plugging both numbers back into the original equations. 3 times 2 plus 4 times 1 equals 10, and 2 minus 1 equals 1. Both statements are true, which guarantees you have the right intersection. Now, consider a system where no variable is isolated. Forcing a substitution here would lead to complex fractions. Instead, we use elimination because we have matching but opposite coefficients, a positive 3y and a negative 3y. Take a second to look at these columns. If we were to add these two equations together right now, what would happen to those y terms? When we add the equations vertically, the y terms perfectly cancel each other out. This leaves us with a simple equation, 6x equals 18, which tells us that x equals 3. To find the final coordinate, we follow the same rule as before. Plug the x equals 3 into the original top equation. This gives us a y value of 2, locking in our intersection point at 3, 2. Occasionally, you'll run into a system where both variables disappear during the algebra. This isn't a mistake. It tells you something specific about how the lines are positioned. A false statement like 0 equals 5 means no solution. The lines are perfectly parallel and never touch. But a true statement, like 3 equals 3, means infinite solutions. Both equations describe the exact same overlapping line. Use this guide to keep your steps organized. Start by choosing the method that fits your coefficients. Always make sure you solve for both coordinates, and always verify your final answer by plugging it back into the original system.